at this point at which we discussed so-called diffuse interface approach. So once again, there is a sharp interface approach to modeling, and there is a diffuse interface approach to modeling. What is the difference? The difference is in thickness of the interface. In sharp interface approach, we use zero thickness of the interface, the sharp interface at which we establish discontinuity in the for the fluxes. Difference in fluxes leads to the interface velocity, and we consider two bulks: metastable bulk, like here we say at 0 of the order parameter, and stable phase at 1, which characterize the ordering crystalline structure. So this is a homogeneous liquid, this is a solid. 0 belongs to the metastable phase in the case of dotted line. And here we have 1, the state with lower energy, which is divided with this metastable phase by a special barrier. And then we have to go from metastable to stable phase through the barrier to attain the stable phase. So, and we have, of course, special equations in liquid and solid in the case of sharp interface, and we have now this area. This area shows us diffuse interface. In principle, we use sharp interface when we can neglect the processes at the interface. But in reality, we have, if we have driving force enough to provide non-equilibrium effects, for instance, disorder trapping from the liquid, solute trapping from the liquid, or decreasing degeneration of solid drag, then we have to use this diffuse interface between phases. Because at the large driving forces, we have high velocities, and these high velocities provide to trap, to catch the inconsistencies existing in the homogeneous phase. We know that this homogeneity is only on the macroscopic or mesoscopic level. In reality, we have clusters in liquid, and between these clusters there are voids, there are defects, and then, of course, if we have large enough velocity, we trap these inconsistencies, imperfections, and then these imperfections build up not ideal crystal structure. And in order to have relaxation to more stable locally equilibrium state, we have time. We have time for a relaxation of defects, but if the interface moves with the high velocity, then this time is not enough in order to relax to local equilibrium state at the diffuse interface here. So, and how we can characterize? We can characterize macroscopically by the order parameter phi, And this order parameter changes from 0 at the metastable phase to the 1. On the microscopic level, we have a transition from completely disordered state. Atoms are disordered, atoms or clusters are disordered, and they move everywhere, and we have 0 value of order parameter. However, if we go to the solid state, we see that our rows becomes more and more ordered, and then we got ordered rows of atoms with maxima in atomic density. This means we arrive to the ordered state in the solid phase. Energetically, it could be seen in this picture. At equilibrium temperature, Tm is melting temperature. So at the equilibrium temperature, we have 2 states with equal energy. However, if we decrease temperature below the melting temperature, state with 0 liquid state becomes metastable, becomes with higher energy than stable phase. Therefore, we can construct homogeneous part of this free energy, and then plus summarize with terms which are responsible for these inhomogeneity. We now consider the equations and terms responsible for the fast transition to equilibrium. So at small driving forces, in diffuse interface approach, at small driving forces, we have a direct proportionality between change of the phi of the order parameter and driving force. So as soon as driving force derivative, variational derivative of free energy with respect to phi exists, then immediately and instantly we have a response. Variable is changed in time as soon as we have these driving force. This is for non-conserved variable for phi, for instance, for the phase field trajectory as a maximum of amplitude, envelope of maxima of amplitude. For instance, if we have a transport process of atomic transport, we have to take into account that we have a diffusion flux, and this also instantly proportional to the driving force, to the gradient of chemical potential. And then we have 2 equations which can be used for description of our system at small driving forces, not far from equilibrium. However, if we have large driving force with far from global equilibrium and the local non-equilibrium, then we have to take into account all contributions from the past. And instead of this instant equation, we have change of order parameter in time due to the integration from the past, from minus infinity to the current moment time, t, and then we have memory t in this case, and also we have a variational derivative with respect to phi from the free energy, and all these terms plays essential role in the evolution of our order parameter. Minus means that our order parameter relaxes to the equilibrium. So in the case of we have diffusion of atoms, we have also taken into account that our diffusion flux relaxes to equilibrium through the prehistory, through the memory kernel MD and gradient at T star. So we have to integrate from minus infinity to the time t, and then we have this equation together with mass balance, which gives us a special type of equation if we use special type of memory function. So which memory functions are known and well established with a constant? If we have constant m phi, then we have wave equation. If we have delta function of memory functions, then we have dissipative propagation, which described by the parabolic type of equation. This or Landau non-conservative order parameter for the moving of the interface. If we have so-called Maxwell-Cataneo-Vertanet function, which shows us that we have relaxation to the equilibrium in kinetic parameters by the exponent, then we got so-called telegraph equation, which combine wave and dissipative propagation, and this is a so-called hyperbolic type of equation. There are other components, for instance, dissipation with relaxation, and so on and so on, exponential relaxation with oscillations. But for us, it is important wave and dissipative propagation because this gives us to take into account characteristic speeds of solute diffusion. And if the interface moves with velocity comparable with the speed of solute diffusion, then we are able to see non-equilibrium solute trapping. If we reach or overcome the characteristic speed for the solute diffusion, we can get complete solute trapping, and the structure will be completely disordered and metastable. Therefore, by this type of equation, wave and dissipative propagation, we can describe our system in a good manner to describe at least solute trapping. Normally, also with this type of equation, with wave and dissipative propagation, with this memory function, we can describe also disorder trapping as well, because disorder trapping has the same order of relaxation as the solute trapping. So by the classification of phase field diffuse interface models, we can just summarize our equations in a manner of C model. There is a B, C. A means that we have description for the order parameter with non-conserved order parameter. B is description of the conserved order parameter, and C combines disorder these both cases. So we have a transport of mass. C is concentration here, and we have interface, diffuse interface propagation by this equation. So what they characterize? So this term, first derivative in time for concentration and first derivative in phase field, gives us relaxation of the concentrational field and relaxation of the phase field itself. This term and this term of second derivative of concentration with respect to time and phase field relaxation with the phase field, second derivative of the phase field with respect to time characterize as relaxation of concentration derivative in time and this relaxation of phase field in time with their characteristic times, diffusion time and tau phi, which characterize relaxation of the so-called gradient flow derivative of phi in time. These right-hand sides characterize as diffusion propagation of concentration and also diffusion propagation of the field phi. I would say this is not correctly to say diffusion. This is a dissipative term which shows us propagation of solute diffusion by the diffusion mechanism, and this is also propagation of interface by the diffusion mechanism, because second derivative in space, Laplacian here and Laplacian here, characterized as description of inhomogeneity of these functions C and phi. This term is coupling term, which gives us coupling with this equation. So this is a system of equation which can be solved, for instance, numerically or analytically. Analytically, we can describe phase field. Numerically, we can describe concentration and phase field as a coupling system of equations. There are different methods of solution of the phase field equations. As I told you, analytical methods are based on the search for traveling wave solutions, which normally can be obtained in one-dimensional space. It's the easiest way to get. And there are different methods in order to get traveling wave solutions. This is the first integral method or hyperbolic tongue method. But anyway, this type of solution could be considered in order to obtain main characteristic features of this equation and to be benchmark of 2 or 3 dimensional solutions of numerically. So in 2 and 3 dimensional modeling, we can get by the special numerical methods, for instance, by finite difference method or finite element method, we can get solutions in space and in time. So this is not so important. So traveling wave solutions. These are profiles which characterize as homogeneous state and ordered state, and we can get from this equation, partial differential equation in complete, in the full derivatives by this well-known Halilian substitution. We obtain this equation, and then this equation has a solution as a solution for u dimensionless phi, and this solution gives us the proportionality to hyperbolic tangent. And in moving reference frame, we have x minus ct. C is characteristic velocity of the motion for this kink, and delta is the thickness between these two faces. This is the thickness or width of the diffuse interface. And this equation can be obtained for different cases. For instance, for the direct motion or indirect motion, they are calling as the kink and anti-kink solutions. So in analytical solution, we can get a profile of phi and then consider how we can how the thickness of the diffuse interface changes in space and in time, and this is the envelope, as I told you, of maxima for amplitudes of the atomic density field. Here we have disordered state, and here we have ordered state with the complete correct ordering rows for atoms. If we consider, and this analytical equation could be considered as a solution for the as a benchmark solution. We can, if we wrote down the numerical scheme, we can try to make solving of these equations in two-dimensional or three-dimensional space. We consider and compare their predictions with analytics. This is a very important part of our modeling. After that, after testing or benchmark making, then we can consider numerical solution of our equations. Here we solve these equations by finite element method, and these two pictures shows us two different structures. This structure is called as a dendritic structure or paraboloidal structure in space, and this I would say disordered structure, which can be characterized as a fractal. More specifically, this is a compact fractal structure. So what is the difference between these two modeling results? The difference is in surface energy. I mean, in anisotropy of surface energy. In this case, we have zero anisotropy of surface energy. In this case, we have 1% of anisotropic energy, free energy at the interface. And then if we have absolutely isotropic case, the branches are growing in all directions as soon as they can. Disordered fractal structure we get, or sometimes it calls seaweed structure. In the case of we have anisotropic free interface energy, then we can get growth along the preferable growth directions. And these preferable growth directions are shown in four orientations, crystallographic orientations, and we instead of isotropic free energy at the interface, we can get these preferable directions because we have a fourfold symmetry in this case. As I told you, we have a special type of equations. These equations are hyperbolic in nature, hyperbolic diffusion equation or hyperbolic phase field equation. And of course, we need to somehow confirm this equation on the microscopic level, because normal standard procedure, if you have mesoscopic equations, and then you can take the lower level of your consideration and you have to somehow confirm whether your equations work properly on the microscopic level. Not only comparison should be made not only with the analytical traveling wave solution or with natural experiments, but also with the equations from the lower level, from, in our case, from the atomistic level of consideration. So what we have discrete and continuous method of modeling, atomistic modeling. Discrete method is kinetic Monte Carlo or molecular dynamics model to use, and we have continuous atomistic modeling based on the phase field crystals. And also we have another type of consideration, more fundamental. This is a so-called coarse graining procedure. We consider atomistic structure and divide it in different small boxes which have enough atoms in order to be average statistically, and then we can derive from the master equation special type of continuous mesoscopic equations and compare them with our equations. So I would say that hyperbolic type of equations, which we considered half an hour before, were confirmed in molecular dynamics simulation for the fast propagating fronts and from the phase field crystals as well, from the discrete and continuous modeling results, and also using the standard procedure which is called coarse graining, we can get equations of motion of the hyperbolic type. If we assume local equilibrium in these equations in the coarse graining, then we can get parabolic type of equations for the phase field and for the concentration, which work for the conditions not far from equilibrium, close to global equilibrium. So, and I just summarize our confirmation of hyperbolic type of equations by the solute trapping numerical experiments. So there are two different models. One of them is model which takes into account deviation from local equilibrium at the interface only, and it has only one kinetic parameter, VDI. VDI is a solute diffusion speed through the diffuse interface. V is the velocity of the interface, C is nominal initial concentration, and KE is the equilibrium chemical segregation coefficient. Chemical segregation coefficient is defined by the ratio of concentration in solid and concentration in liquid. And normally, for the standard type of phase diagrams, we have KE, equilibrium solute chemical segregation coefficient, smaller than 1, because the solid accumulate atoms in the content smaller than liquid. It's a normal case because we have crystal lattice, and this crystal lattice has a special energetic state, and in order to build up equilibrium energetic crystalline state, we need to construct special type of lattice. This is energetically more complicated than in the liquid. In the liquid, atoms moving stochastically, and they do not need to take special positions in special places. Because of this, KV is a chemical segregation coefficient dependent on velocity dependent chemical segregation coefficient. And then we have these equations as a function of velocity and interface speed of the solute diffusion through the diffuse interface. So as soon as we have V tends to 0 or V is 0 in equilibrium, we have Ke as a function of, we have a Kv as a function of Ke and solute segregation and concentration. In the case of and this equation has been obtained using the parabolic type of diffusion in the liquid phase. However, if we have a very fast propagation of the interface with large driving forces, for instance, in additive manufacturing or in laser and beam treatments of the surfaces, for instance, in the melt spinning or atomization, electromagnetic levitation, we have several hundreds of undercoolings or hundreds thousand of Kelvin per second and more million or several millions Kelvin per second of cooling rates. Then we need to take into account fast propagation of the interface and local relaxation because impossible ahead of the interface. Because of this, we have to take into account not only solute diffusion speeds through the interface, but also VD, VDB, this is a VD in bulk. So solute diffusion speed in bulk phases as a second parameter of our equation. And if we compare these results with these equations with experimental data, we can see that both curves, solid curves or dotted lines, which are from CGM expression, which takes into account only deviation from equilibrium at the interface, properly describe our data at small and moderate growth velocities. However, if we consider further these equations, these deviate from experimental data, which can be described in very good manner by the equation with two kinetic parameters: VDI, solute diffusion speed through the interface, and VD, which characterize solute diffusion speed in the bulk phases. Therefore, we can say that equation based on the hyperbolic transport equation can describe our data in a good manner from the small up to moderate and large growth velocities for the partition coefficient, chemical partition coefficient. There are different and other comparisons which I do not consider in our lecture. I just want to say that these two lectures were rather complicated for our understanding because we need to take into account special effects. Just a few words at the end, because we have a short lecture today as the end of lecture on analytical description of the fast front propagation interfaces. And as an outcome, I can say that we have considered more or less in details diffuse interface approach to rapid phase transformation, especially to the rapid solidification. And we have considered equations of hyperbolic type, which were considered in the case of solute trapping. And as I showed you, the solute trapping could be described more thoroughly with equations which take into account the deviation at the equilibrium at the interface by VDI, solute diffusion speed through the diffuse interface, and VD. VD is the velocity of the interface. VD is the velocity of solutes in bulk liquid concretely. So, and we can characterize the chemical inhomogeneity by the ratio of solute in solid and solute in liquid by KV, chemical segregation coefficient. So I would say this for today, that's it. Next lecture I will provide about specific features of glass forming alloys formation, because here I consider it only classical case when we have disordered state in the liquid, ordered state in the solid, but there is another class of systems, of mixtures or alloys, which exhibit a special ordering in the liquid state. And these belong to the case of glass forming alloys, glass forming systems, which very good build up glasses. Because for normal pure metals or normal standard metal or metalloid systems, transition to glass is complicated due to the fact that we have disordered state which we need to freeze up, and we have to take very high cooling rates in order to freeze them to the solid state. However, glass forming systems have already some ordering in the liquid, and then we can freeze it with much lower cooling rates to get this amorphous state. Why amorphous state is important for us? Because normally amorphous metals exhibit very good electric conductivity or very good mechanical properties, I told you. So, for instance, in our telephone, in our handy and phones, all specific things are made from the glasses, because glass has a very good electrical conductivity, and these small pieces of our handy or our mobile phones are made from the glasses in order to have very fast and good electrical conductivity. This is a practical outcome from the glasses, for instance. Moreover, glasses exhibit a very plastic properties, or in general mechanical properties, hardness or plastic states, which make the amorphous alloys are very popular among materials research community. So next time we will make lecture about features of glass forming alloys and their solidification. Solidification in English include not only crystallization but also amorphization. So solidification in English language plays a role of general word which includes crystallization and which include also amorphization, I would say. So next time we will pay our attention about to the glass forming alloys. And maybe one of our colleagues, Mikhail Krivelov, also provides some lecture